Hey everybody, it's Ridley. We're back again. All right, so today we're going to talk about limits of functions of multiple variables. Now, notice that we're talking about something entirely different than limits of vectors. This is different than limits of vectors. So you're kind of going to have a little cognitive shift as we work our way through multivariable calculus. All right, the parameterized vector function r of t versus the function of multiple variables f of x, y. This guy exists in 3 space. This guy exists in 3 space, but with a parameter which gives it 4 space. Okay, so enough said. I'll shut up. Let's talk about limits as they used to be. We know that the limit as x approaches a of f of x equals L if and only if for every epsilon greater than 0, there exists a delta greater than 0 such that absolute x minus a is less than delta and greater than 0 implies absolute f of x minus L is less than epsilon. Now, this is the formal definition of limit, and we're going to talk about the formal definition of limits for function of multiple variables as well. So I don't want you to panic, because we knew what this meant. We weren't afraid of this. This was just our dental floss definition of limit, right? If I've got a function, right, and I'm approaching it at x equals a, and I approach from the left, and I approach from the right, if it goes to the same value, then we know the limit as x approaches a of f of x equals L. This is just fancy math speak for that. Okay, now let's talk about our function f of x, y. Now, this is kind of a crazy definition of limit, but I'm going to write it up just so you have it, so we're not afraid of it when we get into our advanced analysis courses. We're not going to use it. I promise you that right now. Okay, so first things first. We're going to, instead of having x go to a, we're going to have x, y go to a, b. These are ordered pairs, predictably. Remember, f of x, y, think about it as always equaling z, right? Of f of x, y equals L if and only if. Now, this is where it gets kind of fun. For every epsilon greater than 0, there exists a delta greater than 0 such that, now here's kind of where all hell breaks loose. If xy is an element of the domain, all right? So in other words, it lives, oh, notice, this is a Snagit from that 3D grapher that I've been using. So if I pull xy from somewhere out of here, let's see if it's going to do it black. I think it did give me a black. I want a blue. Oh, no, it is blue. Let's go red so we can see it. Red. So I'm snagging a value out of the xy plane, okay? See if I'm still, yeah, I'm still back here. Sweet. That's cool. All right. So we're taking xy out of there, and now this is where it gets a little bit crazy. The square root of x minus a squared plus y minus b squared is greater than 0 and less than delta, then this implies that absolute f of x comma y minus L is less than epsilon. Now, let me explain what this is. Because this was in 2 space, when we were talking about the Cartesian plane, this was relatively easy to understand. Remember, we grabbed a delta around x. Delta lived down here, and when we projected it up, we ended up with what I called an epsilon ball or an epsilon neighborhood. Well, in this case, watch this. I'm going to use my blue, well, it doesn't really matter. What is this? What's the square root of x minus a squared plus y minus b squared? That's a circle. What we're doing is we are opening up a delta circle. That's supposed to be a delta, by the way. Sorry about that, you guys. Delta. We're opening up a delta circle, and then we're going up to the curve and seeing if we approach along all of the lines, all of the possible approaches, are we heading for this limit point? And the limit point, notice this z, so this is going to be a z, so this is going to be a z. This is going to be our limit point. As this circle gets smaller and smaller and smaller, we get closer and closer and closer to that limit point. Just like in 2 dimensions, we don't have to hit the limit point. Let me be really clear on that. I'll say that again. We are not hitting the limit point. Now, I can't do the dental floss thing. Well, I reckon I could, right? I could just strap the dental floss right through the middle of the figure. Like we're ignoring that, or just, I don't know, what's a better way to do it? Like a toothpick, right? Poke a hole in the figure. Don't care about what happens at f of xy. We only care about what happens arbitrarily close to xy. Okay, that is the theoretical introduction to limits in 3 space. Okay, I told you before, I'll say it again, we're not going to use this definition, but I do want those of you that pop into the analysis courses to have seen it, and I want you to get an idea about how limits work, because if you think about it, rather than having this really clearly defined way to approach x equals a, I can only approach from the left, or I can only approach from the right. Well, when I've got a circle, when I'm reeling in this this radius of this circle, I can approach from uncountably infinite number of ways. And that gets a little nasty. That's sort of where the rubber meets the road. And that's what we'll get into here in just a second. Meet me back here in just a second, and I'll get rid of this awesome drawing. Okay, so here we go. Let's talk about the limit as xy approaches ab of f of xy. This is the notation. It's a little clunky, a little difficult to write, particularly if you're using like a word processing document or something like that, or word processor, excuse me. But you'll get used to it. It's just like the limit as x approaches a of f of x. Okay, now here's where it gets a little bit tricky. Remember, if I took the limit as x approached a of f of x, and I'm checking to see if it equals L. Let's put question marks in both cases. Here's my function, f of x. Here is my x equals a, and it appears that this is L. Now, the rules have not changed in terms of how you start this limit. It is always plug it in. Always plug it in, plug it in. It's the first step. Remember, if you get an indeterminate form, all hell breaks loose, but there's a problem. Remember, indeterminate forms were solvable if we used L'Hopital's. There is no L'Hopital's for vectors of multiple, or for functions of multiple variables. So we have to approach it in a different manner, okay? So I'm going to write a function. I'm going to write this guy. F of xy is equal to x minus y, whoops, not x minus y, I want xy over x squared plus y squared. All right, xy over x squared plus y squared. All right, now if I want to find the limit as xy goes to 1, 2 of f of xy, it's a no-brainer, right? 1 times 2 is 2 over 1 plus 4. This is 2/5. I'm happy as a pig in poop. Nothing to it, okay? However, what if I want to take the limit as xy approaches 0, 0 of f of xy? Now I'm in trouble because I plug in 0 over 0, I'm dead. I cannot use L'Hopital's on this. There's no way to do that, right? Because I've got a function of 2 variables. Now, in our next lesson, we're going to talk about something called partial derivatives, but partial derivatives don't work with L'Hopital's. So what I have to do is, let's take a gander at it first, just like we did before, okay? I'm going to look at the graph itself, and then we're going to talk about some options. So meet me at the graph here. All right, let's move this guy over. Whoa, look at that thing. Holy smokes. All right, so something's going on. Notice this is this point right here. Let me get this thing out of here a little bit farther. Okay, this thing, these spikes, this one appears to be at 0, 0, or depending on how this thing is graphed, like it may be connecting points, but that's pretty rad to look at. Let's just take a minute with that. Wow, look at that. I love it. All right, so when I've got it like this is 0, 0 at this spike. I'm assuming it's also 0, 0 at this spike, so we've got something weird going on here, and I can't really tell by kind of looking into the thing. I don't know how, right? There's just not enough detail. So I'm going to write a definition that comes straight out of your textbook, and it's going to seem pretty straightforward, I hope. But what I want you to think about is when I'm taking the limit as x approaches a of f of x, so I'm in the plane, when I take that thing's limit, I only have 2 paths. I have the limit from the left, and I have the limit from the right. And remember, there was another way to define a limit. If the limit as x approaches a from the negative of f equals the limit as x approaches a from the positive equals L, then that implies that L is the limit. L is the limit. In other words, if these things exist. You with me? All right. There's a problem, though. If you recall from what we talked about over here, there's an uncountably infinite number of quote-unquote paths. So what we do is we go on a fishing expedition. And let me write this out. This is coming straight out of your textbook. It says if, I want you to have it, though, f of xy approaches L1 as xy goes to AB. I don't really need this. I think we all know what I'm talking about here. Along a path, along, let's say, C1. All right. Now, that path would be, remember from the graphic, that path would be one of those paths coming into the center of the circle, where the middle of that circle is AB. Okay, along that path. So we got this. And f of x, y approaches L2 as xy goes to AB along a different path, along C2. So that would be along some other path, all right? So if that happens, can you kind of see what's going to happen? Along one path, not so much from the left, but it is sort of like a two-dimensional examination of what's going on in one dimension along the x-axis here. If I approach from the left and I get a different value than when I approach from the right, well, we know that the limit doesn't exist. Same thing here. If I can find two paths where their limits do not approach the same value, this implies that the limit as xy approaches AB of f of xy does not exist. Okay? Okay, so let's try and do this limit really quickly at 0, 0. We're gonna do this guy. So I'll pop over to the other page. Excuse me. So let's see if we can figure this out. Let's take the limit as xy approaches 0, 0 of, what did I say, xy over x squared plus y squared, I believe. Excuse me. All right, so let's pick a path. Now, we already know what this thing looks like, but let's just pick a path. How about let's let x equal 0. So let me go back to that. Let me go back to this guy. So what I'm saying is, I am going to, I don't think it, I'm going to have to grab my Snagit again. You guys can see how I do this. Let's go new. I'm going to grab this guy. And now I've got it. Now watch this. So I am picking the path along x equals 0, which we know is the y-axis. So I'm fixing x equals 0, and I'm going to see the behavior of this thing. Okay? So let me pop back over to here. Let's go, what the heck? Let's go here. Let's move this over here. Okay, so let x equal 0. So if x equals 0, then this implies the limit as xy approaches 0, 0 of, well, what do I get? 0 times y over 0 squared plus y squared, which, well, that should be relatively obvious that that equals 0. Okay, so we have a path and we have a limit. Sweet. The limit exists. We have a number that we can actually hang our hat on. Well, similarly, why don't we fix y equals 0 and see what happens there? Well, if I take the limit, so we're going to let y equals 0. All right, and I'm going to take the limit as xy approaches 0, 0 of, now what's going to be? It's going to be x times 0 over x squared plus y squared. And this is equal to what? Well, crud, 0. All right. Damn, this just doesn't look like it's got a limit, though, does it? The problem is we've only checked 2 of an uncountably infinite number of points. So what if we were to say, well, how about I just let it be a line, all right, that passes through 0, 0? Well, how about y equals, wow, that was not in control at all. How about I just let it be y equals mx? Now what would happen? Well, let's see. Let y equal mx. That passes through 0, 0, right? We agree with that. That's another path to 0, 0. So I'm just checking this one because this makes me nervous. Only having two things is, I can't generalize, right? All right, so let's see. Let y equals mx. This implies the limit as x comma y, and I could say x comma mx if I wanted to, just like I could say x comma 0 here and 0 comma y here. All right? Where am I? I'm sorry. Let's plug in y equals mx. So what do I get? I get mx squared over, what do I get? I've got y equals mx, so this is going to be x squared plus m squared x. And this is going to equal the limit, well, let me come down here. This is going to equal the limit as xy. I forgot my goes to 0, 0 over here, didn't I? What a ding-dong. Goes to 0, 0 of, well, mx squared over x squared times 1 plus m squared, isn't it? Now what it would give me? X squareds cancel. I have no y's, I have no x's. As far as this limit is concerned, this is just one big constant, which is m over 1 plus m squared. Well, we can't let m be 0, because if I let m be 0, then y equals 0, and we've already tested that. This is a constant. And this is a constant that's not equal to 0, which implies the limit as x, y goes to 0, 0 of f of x, y, which is this guy, does not exist, which our intuition probably should tell us on this guy. All right, now we got limits. You know what's coming next, folks. What were the cornerstones of Cartesian calculus, of planar calculus? We started with limits, then what did we move on to? Oh, you guessed it, folks. How about I meet you over here in just a sec with a big screen and we'll talk about continuity. Oh, and guess what else is coming? Derivatives. Derivatives, you say? How is it possible that we could take derivatives in 3 space? Well, we're going to talk about that. That's actually next lesson, but meet me back here in just a second. We'll talk about. Okay, so let's talk about continuity of f of x, y. So really, we're just talking about z. We're talking about a function. No big deal. You can probably predict. Remember, back in 2 space, back in the Cartesian plane, we said that if the limit as x approaches a of f of x is equal to f of a, that implied that f is continuous at x equals a. And then we said that f is continuous if it is continuous at all values in its domain. Whoa, what just happened there? Sorry. Joules, whatever. Sorry, feeling a little giddy. Just had lunch. At all values in its domain. Okay, in its domain. Wow, maybe I had too much lunch. All right, so what do you think? How do you think we're going to discuss continuity in terms of functions of multiple variables? Well, that's just if, wow, I'm over here on the scene, if the limit as x, y approaches ab of f of x, y equals f of ab, this implies f is continuous at ab, x, well, let's just say ab. Now, similarly, if f is continuous at all ab in its domain, remember that domain is the xy's in the xy plane that works, that implies that f is continuous. That's it. That's continuity of a function. Now, there's a bit of a trick here that we got to be careful with. Remember in 2 space when we had f of x, I keep saying remember. Remember in 2 space when we had f of x equals, let's go x squared minus 4 over x minus 2, right? And we know that the limit does not exist at x equals or excuse me, we know that the function doesn't exist when x equals 2. So f of 2 does not exist. It punches a hole, right? Because I can do a little bit of algebra and I get x plus 4, oops, x plus 2 over x, or times x minus 2 over x minus 2. So I get this guy, x minus 2 over x minus 2, and I punch a hole. And this guy behaves, we should actually use an implies arrow, right? This behaves like x plus 2, except it's got a hole at x equals 2. Now, if you recall, we could fix that hole, we could fix that discontinuity by saying let f of x equal to, and then we're going to describe it as x squared minus 4 over x minus 2 for all x not equal to 2. And then we're going to describe it as what? What should it be when x equals 2? Well, I plug 2 into this guy, and I get 4 when x equal to 2. And what that does is that effectively plugs the hole at x equals 2. Now, look at this function. Look at this guy. Now, we had this place where the limit didn't exist, but it didn't exist, there's no holes to plug. There can be holes that we can plug if I have algebraic cancellation in this guy, but it's far more difficult. It's much more tricky because those discontinuities aren't created because of holes. Typically, they're created because of lack of limits. So that's it. That's it for this section. We've got limits and continuity, and you guessed it, we're on to derivatives here in no time at all. I will say the text discusses limits of more variables, or excuse me, functions of higher variables like x, y, z, but we're going to stick predominantly to 3-space. All right, we'll have brief discussions, maybe some fun extra credit problems that deal with higher spaces, but because they're so hard to visualize and so hard to wrap your brain around, I just want to make sure that we have a good solid foundation in 3-space, and then when we're talking about parameterization, we're talking about 4-space. Okay? All right, well, thanks for your time and attention. I'll see you in class tomorrow.